Hello everyone, I am Dr. Uma Priya, working as Assistant Professor in the Department of Chemical Engineering of KPRIIT. In the previous session, last session, we have discussed about what is reactions and what are the types of reactions we have. Particularly in chemical reaction engineering, the next most important topic is what is reactor and types of reactors. In today's session also we are going to discuss about what is reactor and what are the types of reactors we have. Reactors means it is a container. This container helps to carry over the reactions at that particular conditions. However, the reactions is required to carry over the reactions to convert the reactant to the product. So many factors are involving in this while designing the reactor. What is the material we are using for the reactor design, and what is the cost of the material, what is the character of the material. So these things we have to consider, and what are the chemical kinetics we are planning to maintain inside the reactor. This is the most important factor we have to consider while designing the reactor. We have so many types of reactors. Particularly we have two main divisions. One is batch reactor, the other one is continuous reactor. The batch reactor means this container you can see very clearly. This is the batch reactor. This is the container. Inside we have the stirrer for mixing process, and once if we load the reactant inside the reactor, we leave the reactant for particular time to complete the reaction with the particular conditions however it is required. We will apply pressure, we will apply temperature, and whatever it is required we will apply inside the reactor, and we will maintain for the particular time to carry over the reaction to get complete. And once if the reactant all reacts and converted to the product, we will stop this mixture process, and reactor full entirely will stop it. We will unload the product. Then after the particular time, we will load the reactant and we will continue the process. This is the working of batch reactor. In this, we can get the qualitative approach of the product conversion. Like means 99% conversion, 98% conversion, like that. Accurate level of conversion we can get it because the time duration we can provide it very accurately to convert the reactant to the product. So the next one is the continuous reactor. In this continuous reactor, in the name itself we can clearly mention, once the reactant is loaded inside the reactor, the chemical reaction it will occur inside the reactor. We can maintain the conditions also whatever it is required to carry over the reaction, and after the conversion the product it will get discharged and we can collect it. Meanwhile, we will not stop this loading of the reactant. Parallelly, we will load the reactant, we will unload the product. The reactions it will be happening for the entire 24 hours or the shift basis, but this reactor it never gets stopped. So this is the application part of the continuous reactor, so that quantitative level of product reactant conversion we can get it. Like means if we get 100 kg production per day in the batch reactor, here we can get approximately 1000 kg per day of production in this continuous reactor. This is the one of the most important application point of continuous reactor. Here we can see what are the difference between we have batch reactor and the continuous reactor. Batch reactor, it is very easy to design, it is flexible, and the conversion is also very accurate. And in this continuous reactor, this is continuous, right? So we can't get the qualitative level of like 90%, 98% of highest level of assay level product we can't get it, but we can get the quantitative level of production high in the continuous reactor. And this is the complex flow, and this is like simple flow. Once the reactant applies, no need of stopping anywhere, right? So it will be keep on continuing. So this is not easy to control, this is easy to control. And the next one is in the continuous reactors itself we have so many sub types. First one is tubular reactor, the second one is fixed bed reactor, third one is fluid bed reactor, continuous chilled tank reactor, and the last one is heat exchanger. In the tubular reactor, here you can see very clearly, here inside the reactor chamber we have n number of tubes. So we can provide the reactant in one side. While passing the tube from the one end to the other end, the reaction it will take over, and the reactant it will get converted into the product. While reaching this end size, end section, this reactant it will be converted into the product. So we can see the tubes, n number of tubes inside the reactor, right? So that we are naming this one as tubular reactor. Tubular reactor level, we can get the high quantitative level of product conversion in this. So in the heated pipe itself, or like pipe itself, we can convert the reactant into the product level. So this is the one most important application of the tubular reactor, and we can maintain the uniform conditions also throughout the reactor, because we are providing the temperature through the reactor. At the all point we can maintain the same amount of temperature. There is no need, no variation in the temperature range inside the tubes. So this is the one most important application, and the example of this is steam cracking of ethane, propane, everything is example of this tubular reactor. By using the tubular reactor we can provide this ethane, propane and butane through the steam cracking. Steam will provide in the outer layer of the reactor. The next one is fixed bed reactor. Here you can see one bed. This bed is fixed, right? So we are calling this one as fixed bed reactor. This is the packing material. This packing material, it may be a stone, or it may be a polymer, or it may be a glass, or whatever it may be. This is fixed, and we can provide the reactant from the bottom side, and we can provide the reactant from the top level also. And if we provide the reactant same like here shown in the bottom side, and this is the diffuser. Through the diffuser, the reactant uniformly it will spread into the bed, this fixed bed, and the reaction it will be carry over here, it will be happening here by crossing from this place to this place. This reactant it will get converted into a product level, and through this pressure from the bottom to top we can collect the product in the top level. So this is the example for the fixed bed reactor. Through by using the fixed bed reactor we can provide the naphtha through the catalytic reforming. And the next one is fluid bed reactor. Like we all know about the fluid, right? Fluid, it is easy to flow. It has the tendency to flow, right? Same like this. Here also, same like the packed bed. Here we have packed one packed material, and this packed material it is just like this as shown in the figure. We have packed it, okay? And we are applying the compressed air or liquid from the bottom level through the diffuser, and with the high level of compressive force, this fluid, either it may be the air or liquid, it will go and hit this part, right? By that time, whatever the velocity this air or liquid it has, the same amount of velocity this air or liquid it tries to pull that solid material also after the particular time. After the particular time, even though it is stable at the starting level, after the particular time this packing material it just increases this height. By increasing the height, the n number of gaps it will be happening, right? By that time, if we apply the reactant, this reactant it will go and stay inside in between this solid material, packing material. By that time, if we apply the conditions whatever required to carry over the reaction, this reaction that time it will be happening here. Like this, the collision or whatever the exchange level or combination reaction, everything it will occur here. By that time it will get converted into a product and it will reach the top level. And while reaching reaching the product to the top level, we can maintain the uniform velocity inside the reactor. We can collect the product. Once we are all the product collected, we can reduce the velocity level and we can allow the packed material to stay back. So this is the application of the fluid bed reactor. And the next one is continuous stirred tank reactor. In the name itself we can see continuous, right? So already we have seen about the continuous reactor. This continuous stirred tank reactor also one of the type of the continuous reactor. So in the continuous stir, here we are using the stirrer and we are using the reactor continuously. The process is happening, not like a batch reactor. Once the reactant enters, the reaction will start, and after the particular time it can be converted to a product, and this reaction never stop in the continuous process. Again parallelly the reactant will be flowing inside and the product will be discharging through outside. So this is the continuous stirred tank reactor. Stirring process, reactant intake and product outlet, everything will be continuous inside the reactor. So this is the example of the continuous stirred tank reactor. This is the plant view of the continuous stirred tank reactor. Then one of the main application of the reactor in the field, chemical field, is heat exchanger. Same like the tubular reactor, we have so many types of heat exchangers: shell and tube heat exchanger, double pipe heat exchanger, single pipe heat exchanger. Everything is just like this one only. Like we will allow the temperature condition inside the reactor, we will maintain it, and the reactant it will be flowing inside. After the particular time, the product it can be collected outside. And even the water also, hot water or cold water, everything it will be passing through the shell side or tube side. The reaction it will be happening. So this is the one of the most important application of the reactor in the chemical field. So that I have kept the clear diagram here. See, once SO3 gas from catalyst bed at 700 Kelvin is allowed to enter inside, this is passing through the tubular side, and while passing itself it got converted. So this conversion is like SO3 cooled to 420 Kelvin, 700 Kelvin to 400 Kelvin. The cooling process was completed and we can collect the SO3 here. And by the same time, the shell side, SO2 and air exists. SO2 and air from tower to at 350 Kelvin and exists at 630 Kelvin. Here the temperature increase. Like this, within the particular container, once the reaction occurs at the particular condition, if the container allows to happen that one, or temperature differences happen inside the container, those things are coming under the reactor. And some advancements we are keep on implementing in the design of reactors. Like now the most important like advanced version is micro reactor. Micro reactor means like a small kind of chip what we are using in the mobile and our electronic boards. Same like that we are trying to maintain the reactor also in the micro level to increase the effectiveness and efficiency of the product reactant conversion to the product level. So this is the one of the most important advanced level. Now the chemical engineers, they are trying to concentrate on the research area. And with this we are concluding the reactors and the types of reactor session. We will see in the next session about the what are all the reactors applications we have in the chemical plant. Thank you.